Ich freue mich, zum zweiten Mal hier in Tampere vortragen zu dürfen. Vor einigen Jahren war der zweite Workshop, der ein hohes Niveau gesetzt hat und so reibungslos organisiert war wie dieser Workshop in diesem Jahr. Und ich freue mich und möchte mich ganz herzlich bedanken bei den Organisatoren, den Kollegen Erki Liski und Simo Punternen, dass ich wiederkommen durfte. My talk today is on rotatable design, rotatability, and it's joint work with my esteemed chairman, Draper, and with my esteemed colleague in Augsburg, Norbert Gaffke. I will regress on the first seminal and original paper on the subject by George Box and Hunter in 1957, and in contrast to the presentation of Professor Neudecker, it's the box and not a box. The paper appeared in the Annals of Mathematical Statistics and it's almost 50 pages long, and it's a pleasure to read. The authors introduce the notion of response surfaces, they introduce the notion of rotatability, they investigate the property of rotatability, they come up with designs which you can actually implement. So all those of you who know the paper probably will enjoy spending another 30 minutes on the paper with me now, talking on the paper. And those who do not know the paper, I hope next time you go into the library and you find some time, you may be curious enough after the talk to take the paper and have another look at it. So the background are linear models and used to model response surfaces. We have experimental conditions T, which come from a set script T where we can choose from in m-dimensional space, so that's an m-way problem. We have m variables that we can adjust in order to carry out our experiment, and the ideal condition is such that we get a response surface which can be modeled with unknown parameters theta in a linear way depending on these experimental conditions T. There's a constant here, then we have the linear term, then we have the pure quadratic terms of the experimental conditions Ti squared, and then we have the mixed products Ti, Tj for I smaller than j. We can assemble all the terms that come with a T. Here's a 1, there's a Ti, the linear ones, the square ones, the mixed products, into a big vector which I shall call x of t, and which is the regression vector. That's a big thing where the T is blown up according to the powers that we incorporate into the model. And the parameters over here are gathered together in the vector theta, which is the unknown parameter vector for our model. Now the situation is such that we, for a particular experimental condition TU, so that's each of these TUs is an m-dimensional vector. Our observations have an additive error epsilon, and then we know that our classical linear model theory is applicable, and the important quantity from the design point of view is the moment matrix M, which is formed in the following way. We have a total of n observations, so we give weight 1 over n to each individual term, which is then summed up, and the terms are made up out of these regression vectors. That's a column vector times a row vector, and we sum over all these possible vectors. So we sum over all these possible rank 1 matrices. So again, the important thing is the T itself is a small vector, has only m components, and we blow it up because we have a second order model, third, fourth, and so on. And we blow it up to a big vector, which I take to have k components, and in any particular case we can compute the k, what the value is. Now the approach of Box and Hunter was to look at the response, at the variance surface. The variance surface is the function, the variance function that we obtain when we estimate the response surface. Let me remind you, this would be the true response surface if we knew everything. We don't know the theta, so we estimate it, and then we get this as a variance of the estimator. And if we disregard this normalizing quantity up front here, we obtain what I'm going to call the variance surface or the variance function. Depending on the experimental conditions T, and depending on the model which we choose and which is goes into the moment matrix, we obtain this quadratic form that we are going to investigate. Now, when the model is bad, the variance will go to infinity, and that's difficult to draw and to graphically depict. It's easier to take the inverse of the variance function or variance surface, and that's the information surface. And we're going to look at the information surfaces in some particular cases to get a feeling of what they look like. When we have two experimental conditions, so the little m that I showed before is equal to 2, and these are the 9 design points, then this is a typical information surface. We see that we have 4 peaks here, and the information goes down as we leave the region where the design is being implemented. The typical behavior of this mountain is easily understood when we slice it and look at the contour lines. Here's the same mountain. We see that these are the 4 peaks, and in the middle we have a crater, and this looks very peculiar. One property which is desirable is to have more symmetry in the appearance of the information surface. And one notion of symmetry which is of interest here is rotatability. This is a rotatable response surface because as you rotate it, nothing happens. You can rotate as long as you wish. Here are the contour lines. These are rotatable, and it means that the value of the contour line, the value of the information, only depends on the distance from the origin. So this is invariance with respect to rotations, and if we want to describe this mathematically, we need to introduce some orthogonal transformations and claim that something is invariant under the action of these orthogonal transformations. The way Box and Hunter introduced it is that they required that the variance surface remains the same whether we take experimental conditions T or whether we rotate the experimental conditions by an arbitrary orthogonal matrix M. That's the definition of rotatability in that paper, and that's the thing that is intuitively accessible in the first place. But when you like to do some computations with it, one has to go back to the moment matrix. The moment matrix was the first quantity and the quantity that I emphasized in the beginning. So how do we manage a transition from the variance surface down to moment matrices? Well, there are 2 steps. The first step is that we have to go from the experimental conditions T to the regression vector X. And the statement which I've written here, the equivariance, says that we can go either way. We can take the experimental conditions T, rotate them, and then form this big regression vector X. Or else, if we choose to go the other way, we can take the experimental conditions T, form the big regression vector X, and then appropriately rotate this big vector. Appropriately means that given the little r, I can compute a big rotation, a big transformation, so that these 2 approaches, these 2 avenues lead to the same goal. Now, rather than looking at the abstract statement, let me show you an example. When we have 2 experimental conditions and a second order model, we get a regression vector of dimension 6. Now I'm going to choose a particular rotation. This one leaves the first axis fixed and the second axis is flipped around because the sign is changed. So what we require is that we apply this to an arbitrary vector T and then compute the regression vector. What do we get? This is the constant. T1 is not changed. T2 has a different sign. T1 squared is the same. T2 squared has a -1 squared in there, so that's +1. And the mixed term also changes the sign. And I want to express this as a linear function of the regression vector with a non-transformed T. That's the non-transformed regression vector, and it's evident that I can do that if I choose the big Q in such a way that I get 2 -1s in these places. So besides the notion of rotatability, which is bound to the idea of a variant surface, we can now look at the moment matrices. And when the regression function is transformed in this way, the moment matrix is transformed in this way, that this big transformation walks out up front and goes out into the back with the transposition. And another notion of rotatability is that we require that the moment matrices are invariant under these transformations. Now, in the original paper of Box and Hunter, this is expressed over here. Up here we have the variance function which is not transformed. Down here we have a variance function which is transformed by the rotation r. And the r to the square brackets d is what I denoted by q sub r. Now the idea is if the variance function remains the same, now we want to make the transition to the matrices, then the matrices should be invariant, so that the notion of rotatability as it applies to the variance surface is the same, is equivalent to this notion as it applies to moment matrices. And what the authors say here is a dry whence, and I'm going to talk about this whence. Now that I talk about this whence is somewhat the fate of third generation epigones, because what happens when an important paper is written, there's the first generation, which is the colleagues and people and contemporaries who read the paper. And they find the paper is important, so they start the second generation, which is they give it to their PhD students, and they're supposed to work on a particular theorem. And when this is done, then what is left for me, since all the theorems are already worked up, I can only stick on a particular word. And so I'm going to talk about this whence now. And the problem with the whence is that when you try to write a text critical essay and you talk to colleagues in the law school, they say the first thing you should do, you should clearly state what the authors do not mean when they say whence. So here's what the authors do not mean. What I think they could mean is, in the middle here we have a matrix X transpose X, X transpose X. Now we know that with X transpose X we can generate an arbitrary positive definite matrix if the rank condition is fulfilled. So as an uninitiated reader I could think, well, what's the statement here is, if I have an arbitrary positive definite matrix A and I have another and I repeat it down here with these transformations, then what is stated here, that this arbitrary matrix A is invariant under these transformations. This is what the authors do not mean. And why do I know that they don't mean it? Because I'll show you a counterexample. And what they do mean is clearly indicated in this paper here, because if I erase the A, you see the capital X, and the capital X comes with a small brother, which is the small x. And whenever an author uses capital X's and small x's, I wanted to indicate that these things have something to do with each other. So the correct statement is that this implication, this whence, says that if the x's in the middle are appropriately connected with the little x's out here, then the thing works. And what is appropriately connected? The answer is that we need to use that these x's here are moment matrices of a design. So the statement that is behind the whence is the theorem that for all positive definite moment matrices, rotatability of the variance function, the variance surface, is equivalent to rotatability of the moment matrix. Now, one direction is very easy to show. Let me discuss the direct part of the proof. Step 1 would require, uses the rotatability of the variance function. It says that the variance function of the rotated experimental conditions remains the same. So we can compute that and we get this expression over here. Step 2 is the quick step. Step where I now argue a little bit too hastily. If this quadratic form is equal to the quadratic form on the right-hand side, and this holds for all t, then the matrices in the middle that define the quadratic form must be the same. This argument does not refer to moment matrices, and that's where the flaw is. But if we would have any conclusion like that, then we are in business, because the right-hand side is non-singular, so everything on the left-hand side is non-singular. We can invert these things and solve to get rid of the inverted matrices, and we get this condition, which is the invariance condition for the moment matrices. But if this argument were correct, then we had actually proved a more general statement, because we have made no reference to the fact that we are looking at moment matrices, and we would have this more general statement that for all positive definite matrices, whether they be moment matrices or not, we would have this inclusion, and that's not correct. Here is a counterexample, and unfortunately the counterexample, if you think about it, can only work if you have at least two experimental conditions, so the m is equal to 2, and a second order model, and with this the moment matrix is a 6 by 6 matrix. So in order to find a counterexample for this implication which I indicated before, we need to fiddle around, play around with 6 by 6 matrices. Now when I was a student in my logic class, the professor said that a lot of people claim that they can manage more than 3, 4, 5 variables at the same time, but he as a logician would declare with the authority of a German professor that the greatest number of variables anybody can think about at a given time is 2. So now there's a dilemma. If I'm by myself and I can only handle 2 dimensions, what is the solution? What can I do? And I showed you that in the first transparency. I team up with 2 co-authors, and then we can handle 6 dimensions. So here's a moment matrix which is known to be rotatable, and the inverse is known too, so we can write down the inverse. We know this matrix as it stands here is positive definite, so when we perturb the entries by a small amount, we will maintain positive definiteness. The trick is to choose the right entries to change by a small amount, and what works is the following one. These 2 entries, when we form the quadratic form that comes with this matrix, we get 2 times epsilon, that's 2 times epsilon, and then the terms that come from the regression vector, and this line here corresponds to the T1, and this corresponds to the T2, so we get 2 epsilon T1 times T2, minus, and then we get 2 times this contribution here, that's 2 times epsilon, and the first row corresponds to the constant 1, and the last row corresponds to the mixed term T1, T2, so we get minus T1, T2, these 2 terms cancel, and the variance function doesn't depend on this perturbation at all. We can do what we want, we get the same variance function, we can actually compute it, it's down here, and it's obvious that it is rotatable. It depends only on the distance from the origin through the squared length of t. So any one of these variance surfaces is rotatable because they don't change. They are actually the same. But of course the matrices A here change because we have these epsilons here. And one can ask, what does a rotatable matrix look like? And the answer tells you this is not one. Well, we don't need to dig that deep. We only have to only have to exhibit one transformation so that this invariance condition fails. And I gave as an example the rotation where we leave the first coordinate and flip the sign on the second coordinate. If we take the corresponding q, which I showed as an example earlier, we compute this product, we see that the third row and the third column get a different sign, so the epsilon changes in sign. There are zeros over here, so nothing changes in the first bit. And these 2 also change their sign, so we get a plus epsilon here, and we get the same A matrix, but now with the slight perturbation minus epsilon, and the 2 things will not be equal unless the epsilon is equal to 0. And if the epsilon is equal to 0, we get these things which we know that they are moment matrices. So the trick really is to dwell on the property of being a moment matrix, and here is this hastily quick step 2, which I've now cut down into 4 steps, A, B, C, and D, which I hope I can explain to you how it works. Somehow we have to put in here that we are looking at moment matrices, and that's happening immediately in the first step. I claim that if we are to compute the trace of this product here, we get the result is equal to K. These are K by K matrices, so we get the number of rows or the number of columns. And the way how it works is that for this M over here, we insert its representation as a moment matrix. That's the step that it had no analog earlier. Here we make use of the moment matrix property. Then we use the invariance of the rotatability of the variance function. We get the trace of M to the minus 1 times M. That's the identity, so we get the K. Step B is one on the transformations that play a role. I already mentioned that the transition from the R's, which is a rotation of the experimental conditions, to the big Q's, which are rotations of the regression vector, is an equivariance transition, so it's a group homomorphism, and it means that if we take the inverse of the matrix, of the big matrix, we can represent it as a particular transformation that comes with an inverse of the small matrix, and that since the R is orthogonal, we get R prime in here. And that's easy to check by the properties that we required earlier. Now, step little c, we take the same matrix which we looked at up here and take its inverse. And the claim is that again the trace of this matrix is equal to K. And how do we do that? Well, we can, everything here is non-singular. This is what we got from the earlier step. The Q here is non-singular, so we can invert this. We get this expression. By step B, we know that the inverse of the Q matrix can be written as Q of the inverse of R. So we can insert this in here. And now we see we have the same expression that we looked at in A, except that with the rotation R has now been replaced by the rotation R prime. But if R is orthogonal, so is R prime. And referring to part A, we again get same trace, which is K. And now comes the final step. We define the matrix A in this way, in this form, which is the matrix that appeared up here, except that we are chopping off 1/2 exponent in the back and put it up front. So this is a symmetric matrix. It is also positive definite because all these matrices have full rank. And when we compute the trace, we can wrap it around to the back and refer to part A. The trace is equal to K. And when we look at the inverse, we have computed in part C that the inverse also has trace K. So now we need a little matrix lemma. We have a positive definite matrix whose trace is equal to K, and the trace of the inverse is equal to K. And I contend that the only matrix that does it is the identity matrix. Don't define the identity matrix in this way, because nobody will understand what's happening, but it's easy to prove. And how do we prove it? We look at the eigenvalues. Let's look at the sum of the eigenvalues plus the inverse eigenvalues. The first thing here is the trace of A, plus the sum of 1 over the eigenvalues is the trace of the inverse matrix. Now we know that the first term is equal to K, so is the second, so the sum is equal to 2K. But the function which takes a positive lambda into lambda plus 1 over lambda is like a big bathing tub, and has a minimum value 2 exactly at lambda equal to 1. So we know that this sum is bigger than or equal to 2K, because we have K terms here, and each term is bigger than or equal to 2. Actually, this minimum is attained, so each term which is summed here must attain the minimum. Each lambda sub j must be equal to 1, and if all the eigenvalues are equal to 1, the matrix is the identity. So we know actually that our complicated matrix A here is the simplest thing we can think of, next to 0. That's the identity matrix. And if we pre and post multiply, we get this statement, this property which was the missing link of step 2, and that completes the whence of the original paper of Box and Hunter. Let me show it to you again. Norman, you are so good at sorting out transparencies. Here it is. So the whence here should be read in the way that if the matrix here is a positive definite moment matrix, then indeed rotatability of the variance surface implies rotatability of the moment matrix. Now the real interesting thing is if one can put this into a more general context. This is what we talked about yesterday in the session on rotatable designs. We came across this problem when we started to represent the second order models in a different way than is done in the Box and Hunter paper. So the real fun is, and I think the way we developed a feeling for this problem and its solution is if you look at it in a more general context, but cutting it down to this classical situation, I hope that the solution is intelligible. Thank you very much for your attention.
Thank you very much. We have a couple of minutes for questions to either of our speakers. Anyone wish to jump in? A short question? Baffled them with... okay.
As far as I understand, you use this fact that this matrix is a moment matrix only in order to get these two trace qualities.
Correct.
So, is it true that these two trace qualities imply that this matrix is a moment matrix, or actually your result is true for a wider class of matrices which are positive definite and have this trace property?
Good question. Next Tampere workshop. I don't know.
Yeah, okay, so this is an open area.
Shah?
Small historical correction. This concept is first introduced in boxing in 1951. Rotatability was introduced in 1957.
Box and who?
Boxing with
Yes.
DLSS.
Yes. Mm-hmm. But what Friedrich said about it was correct. So.
No, he said that response statistics were introduced. The correction is
But it's a pleasure to read the paper, and we should not distract our audience.
they are both very pleasant papers.
Yes. Well, actually, that Box and Wilson will be featured in a book of famous papers shortly.
How good a design is if it is rotatable? I mean,
Don't ask me the question.
it's a joint paper, I think. No, I mean, what does it give? What does it offer if it is rotatable?
It gives symmetry in a way which is very easy to understand and which in some situations is very desirable. There may be other situations where other things are desirable, so it's one notion that should be investigated. Sorry?
I want to comment on Nadine's point. As I have thought about the reformulation of the design problem, so as to enable one to say something about the model as well as to parameter estimation. It seems to me that more symmetry is there in the design. The more advantageous it is from this point of view. So, you see, create a strong surfaces with the continuous analogs from the area factorial design. And because of this reason, I am attracted to this area rotatable designs because you see that we have a symmetry. Like you see here, optimal discrete factorial experiment. We have a lot of balance that is coming in so on. So this is analogous to that, and I think that this is a very good starting point to develop the kind of thing that I talked about in the continuous case.
Thank you. Okay. If there are no further questions, then the next session begins at 5 o'clock. Thank you.